So the main idea with 6-6 is when I have a binomial distribution. So if I give you a specific example, it's a little too easy. Can somebody tell me what type of values I'd expect for my x variable if I have a binomial distribution? Now that's a sentence you would only hear in stats class. But what kind of values would I expect for the variable if I have a binomial problem? What does x represent for a binomial? So let me give you a specific example. If I flip a coin 18 times, and I look for the probability that I get exactly 6 heads, right? That's one possible thing that could happen. What are all the things that could happen if I flip a coin 18 times? I could get 1 head, or even 0 heads, 1 head, 2 heads, 3 heads, right? And that's in comparison to what we did in the earlier parts of chapter 6, where like the amount of time it takes to find a parking space, right? At Grossmont, what could that be? How long could it take somebody to find a parking spot? Give me something.
30 seconds.
30 seconds, I like it, right? Or 1 minute and 47 seconds. Or how about 3.894269321111118 seconds, right? Well, they got. What's the difference between I can get 0, 1, 2, 3, 4, 5 up to 18 heads versus I could take 4.9821654 seconds to find out? One is continuous, one's discrete, right? Which one, of course, works beautifully with a normal distribution? Is this a continuous or a discrete picture? Continuous. It is continuous, right? Because what could the z values be? Here's my empirical rule stuff, but couldn't z be 0.4911287? Yeah. Right? So this is a continuous picture. The whole thing was 6-6. The reason that 6-6 gets a little weird is because we're trying to put these rectangles and use a continuous picture to do something with them. That is weird. I can't have 2.9 heads when I toss a coin so many times. If you do, please show me. I want to see that trick, right? You with me? Okay. So that's why I've got to do something to the boxes to make them match up with the idea of continuous. What is it with continuous? What is really that makes something continuous versus what makes something discrete?
Discrete is a number.
It's a continuous measurement of the number.
You got to be careful. I mean, continuous variable could have an exact output. My backpack could weigh exactly 8 pounds. It's very unlikely that it would, but it could be exactly 8 pounds. So what is it truly that distinguishes the two?
The exact measurement available. You can't.
Continuous is not countable.
Can't define.
All right, continuous is not countable, right? There are big gaps in between the possible outputs for a discrete, isn't there? Like we just said, how many heads could I get? 0, jump everything else up to 1, jump everything else up to 2. So it's separated. There's gaps. So in order to make it look more continuous, we say, all right, it's not really 1, 2, 3. It's not 2 here. It's really what to what? 1.5 to 2.5. So I don't use the number 2. I use one of those two numbers depending on the situation. That way, I'm kind of pretending like it's continuous. I'm making it more continuous so that this picture that's continuous works better. So let's do a couple quick, just that type of thing. So this is what I mean. If I said net RMS, I have no idea what the hell that is. All right, if I said the probability x is greater than 7. I don't even know what the mean is. I don't care. I just want to know if this is a NAB situation. What's the NAB stand for?
Normal approximation to the binomial distribution.
Sweet. It's like you looked over your notes. You're fine. It's a normal approximation to the binomial distribution. So I could even call it NAB if I want to, but I don't. How would I draw this? What could it be? If it's 7, there's a bar on 7, right? So what could it be? From what to, or from what?
6.5.
7.5.
Right side.
If I want to be greater than 7, do I want to include 7?
No.
Hell no, right? 7 is not bigger than 7. And which way am I going to shade?
The right side.
I'm going to shade up. So do I want to start here up, or do I want to start there up?
7.5 up.
Do you guys see how to think about that? I desperately want you to understand why we do this.
Okay, I ask you a question.
Sir.
When you do the bell shape, like not, I mean for the not for continuous, don't you always use the numbers before the number anyway in order for it to be for a normal distribution? I thought it was the exact same thing.
For a normal distribution, for a normal, like if parking time, so it takes like on average 7.91 minutes to find a parking spot, and I want to know the probability x is more than 8 or more than 8. Let's just say more than 8. Do I have to do anything that I'm doing over there here? Is there like a rectangle on 8?
Okay.
What kind of data is this? Continuous. It's already continuous. The rectangle is so tiny, it's just like a line. I don't have to do any correction for it, right? Over here, I have truly discrete data. I have to correct for that before I can use a continuous picture to do anything with this. I have to say, oh crap, I better pretend like it's continuous. I better go not 7, I better go from one of these two things, right? So this here would become x greater than 7.5, like you guys said. I don't want to include 7, so I better start at this side and go up from there. Then I would make a z-score out of this. All right, let's try another one. What if it was probability x is less than or equal to 12? You guys try it out. Try to draw a little picture, make a little box, figure out what side to do it.
It's kind of confusing. So, where's how about the area between 7 and 7.5? It's more than 7.
Say again?
The area between 7 and 7.5 is still greater than 7.
But I'm saying that there is no 7. In order to use a continuous picture, the first thing I do is I say there is no 7. There really is just from 6.5 to 7.5.
There is 7.1, 2, 3.
I didn't say that, did I? So this whole bar, this bar right here represents 7. So if you don't want to include 7, you better not include any of that bar. Period. That's the key thing I think that you're missing right there. That bar represents 7, right? And that bar goes from 6.5 to 7.5. So if I don't want to include any of 7, I better start at 7.5. Because that'll capture 8, won't it? What's bigger than 7? What's more than 7? 8, 9, right? And again, this won't be perfect. This is an approximation. It's in the title of the thing, normal approximation, right? And to try to make it even better by going somewhere in between would just be too much work to make it worth your while to do an approximation. An approximation should be relatively quick. That's the whole purpose for doing it. So what do you guys think about this one? So you got your 12. So box on 12. It could be what on that side, what on that side? 11.5 and 12.5. I need a cameraman. And if I want to be less than or equal to it, which way am I going to shade? Down, I like it. And do I want to start then, do I want to include 12?
Yes.
Yes. So do I start here
No.
or there?
There.
Because if I start here, I include the bar. So then what am I going to make a z-score out of? 12.5. Cool. Yes, ma'am.
I'm still confused on why it's that big. Why is it going that way and not that there?
If you have to be less than 12 years old, less than or equal to 12 years old to eat off the kids' menu at Denny's. Younger. Cool. So that's the kind of example I always think about. You have to be at least this tall to ride the ride. That means that or more. So when I see at least, I know I'm going to shade that way. When I see less than or equal to, which is at most, you could be at most 12 to eat off the kids' menu, so you got to be younger than 12. I'm going to shade that way then, younger.
And then the top one is
And if you really want to get to it, which direction does that symbol point? All right, well, that symbol points that way, doesn't it? Isn't that an arrow pointing that way?
Arrow point that way.
And which way is that arrow pointing?
That way.
All right.
So that simple way.
Oh yeah. So in algebra, a lot of you guys learn that once you get past the alligator trying to eat the thing. The quick one is just that points you in the direction of shade. As long as your variable's on that side, it points you which way to shade.
Oh, okay.
Yeah. So if you really want to get down to it, that'll keep you straight. You remember the alligator too? Yeah. Okay.
So on the top one, because it's not equal to, then we start at 7.5 and above.
So then I make sure that I don't include the box that represents 7. I don't want to include 7. I better not take anything that represents 7. Yes, ma'am.
So, because the arrows go that way, and then you shade the middle box or whatever. Even though the x is bigger than 7, so you go from 7.5.
Well, this is put in there later when I was talking about that box.
So 7.5.
I want to start here, right?
Yeah. 'Cause
So
it's
do I
six.
include that box at all at the end?
No.
If I start here and go up, I'm not including the 7 box, which is exactly what I wanted. I don't want to include 7. Okay, cool. Let's do this. Let me do a problem. In the process, I'll show you the shortcut in the calculator for doing binomial problems, right? So I want to fill that hole in. You guys should know me by now. Your answer cannot come from the calculator, but you can check your answer in the calculator, right? So I'll show you how to do it really quickly in the calculator. So let's do a problem. We're going to do it 2 ways. We're going to use the approximation, and then we're going to have the calculator tell us the exact right answer using the binomial. We cool with that?
So do we need the z-score trick?
Oh, yeah.
So to your original statement of when you have a binomial distribution, x values expected, which one that is? X values expected. What you were saying when we started this lecture.
X values expected.
Yeah, when you have a binomial distribution.
Oh, we talked about it. What could your x values be? 0 up to the total number of times you're doing something. How many? Because x represents successes. So how many successes could you have when you do something 18 times? 0, 1, 2, 3, up to 18. That's why it's discrete data. You can't have 2.8 successes. It was almost a success, so come on, right? Sort of like last night's game, but that's all that. It was 0.8 and we'll win. Sorry. I'm not bitter at all. All right. What about this one here? Let's do one more quickie and then we'll do a whole problem out. I personally hate memorizing shit, so I always try to get a way that you don't have to memorize anything. It takes 3 seconds to figure out what to turn this into. You don't want to use the number 50. The problem, I'll say use the nav. I'll say that. So you got to remember, nav means I got to do this continuity correction. Got to move it on one side or the other of the rectangle. So here's your 50. So it could be
49.5.
or
50.
50.5. You want to be less than 50. You want to shade in what direction?
Left.
Down. I love it. Do you want to include 50 or no?
No.
So you don't want to start here then, do you? Because that would include 50 as it goes down. I want to start here so I leave the box out of it. So you would make a z-score. So through the continuity correction, this becomes less than 49.5, right? So then you would make a z-score at 49.5. So here's what we're going to do. I'm going to do this one problem. I'm going to do it several different ways. And I'm really going to try to make it make sense as to what the hell I'm doing. I'm going to do it correctly. Then I'm going to do it without doing this. And then we're going to see what the actual answer is. And if this one is closer, should be. That should make the approximation better. If I didn't do this step, my answer would be way off from what it's supposed to be. That's the whole point. So here we go. Let's say, let's do this. Here we go. 42% of San Diegans give out candy at Halloween.
Did you have a good day, Halloween?
Oh, hell yeah. North Park's cool, man. It took me back to, I live in North Park now. We went a few streets over away from 30th Street, and it was just like my childhood. I'm like, holy shit, this is the way it used to be when I was a little kid. Just kids all over, running all over the place, getting candy. I'm like, man, I remember when that stopped doing that. Anyway, so it's good to see that they're back, at least in some neighborhoods where you can feel sort of safe. Okay. 42% of San Diegans give out candy at Halloween. If we take 68 San Diegans, what's the probability that at least what, Jeff? I don't know. Say 27 will give out candy. Right? So first we'll do it correctly. I want to make sure that we do it first correctly so that everyone can focus on that's the correct way to do it. Then I'll do it incorrectly, and then we'll see what the actual answer is. So what I'm about to do is not wrong, it's an approximation. So it won't be exactly the same answer as if I actually use the binomial distribution like I'm supposed to. Why do I not want to use the binomial distribution, by the way? How many times would I have to use a formula? Because what could it be? X could be 27. I have to do a formula for 27, for 28, for 29, all the way up to freaking 68. Right? Even if I go the other way, it's still got to be 26, 25, all the way. Screw that. Oh, I really don't want to do that. Right? I'd much rather use the normal approximation. So on the test, I'll actually say use the nav. And I'll actually be crazy nice. I will first ask you to find the mean and the standard deviation because you can't do this unless you have those. What do you need to be able to make a z-score? Mean and standard deviation. So I'll have a separate part that says find the mean and standard deviation, which you need for the next part. So how do you find the mean and the standard deviation? What are the parts of this problem? What's n, what's p, what's q? 68, I love it. 0.42. So q must be 0.58. How are we doing so far? The probability does not matter, depend on how many San Diegans I pick. Do you guys see that? If 42% of San Diegans, does it really matter if I pick 68 or 427 or 3? It's still a 42% chance that any San Diegan will do it. So P and Q can't change for a given problem. I always get somebody do like 27 divided by 68 and that's their probability. No. It's got to be this. I already told you what it is, right? I got to give you what P is. So how do I get the mean now? I think somebody started telling me. 28.56. Good. So N times P, right? That's the little mean formula. It's the best mean formula we've seen yet. And N is 68. P is 0.42. So what's the mean going to be? 28.56. Say again? 28. Oh, 28? 0.56? Cool. So you see why I picked 27. We'll make sure that it actually came out to something big enough for us to see. So the mean is 28.56. What's the standard deviation? What's the formula for that?
Square root of NPQ.
Square root of NPQ? I like it. And so you get the square root of 68 times 0.42 times 0.58. Some of you guys realize that this is already n times p. You really just need to multiply that by q and then take the square root. So it makes it a little quicker on the calculator. If you don't like all that business, just put that in. Nothing major there.
How many you get?
So it's like 4.0699. 4.0699.
Yes.
So that's one place where I would take 4.07. That's fine. Yeah. 70, right? How you guys doing here? So far, so good? So this would be like part A on this problem. I'd say find the mean and the standard deviation. And then part B, I'd say use the nav to find the probability that it's at least 27. So when I draw this picture, what goes right in the middle?
Mean.
Which is?
28.
We figured the mean is 28.56, right? So where's 27 at?
Even.
Somewhere over here, right? You don't have to be perfect, by the way. Give yourself some room so you can draw your little box. You see that? Draw your little box. What are the sides of the box? 26.5? 27.5? And if I want at least 27, do I want to include 27?
Yes. Yes.
Yes. And I'm going to shade in which direction? I'm going to shade
To the right.
Right.
to the right.
That's right.
I like it. So if I want to include 27, I don't start here, of course, because that doesn't include 27. I have to start here and go up. Right? So this question then is transformed, and this is the part that I'm never sure if anybody gets this totally. I can't use this number when I want to use z-scores because z-scores are continuous and this is a discrete part of a data point. So I need to kind of correct for that. So before I can use the z-scores, I have to change the question into what we just figured out, 26.5. So what's my z-score formula going to look like?
Z equals X.
All right, x minus the mean over the standard deviation. So z is, careful, 68 is n. What data value am I curious about? 26.5. Minus the mean, 28.56 divided by standard deviation.
4.07.
Coolness. It's like 0.4 or something.
Negative 0.506. That is 5.1.
5.1? Okay, cool. You guys all getting that? And what do I do with this?
Look at that.
So notice, once you figure this out, once you figure out how to change that number, everything's the same. You make a z-score out of it, you look it up, you make sure you answer the question right. When I look up negative 0.51, what do you get?
3050.
3050?
Yes.
Cool. Is that my answer?
No.
You have to subtract from
1.
Exactly. So to get this side, I got to do 1 minus that. And I get 0.695. Right?
Mm-hmm.
How we doing? 69.5% chance. So that's the correct way to do this problem. Now let me really quickly do it wrong. Maybe don't even write this down. Just to be really sure that we don't do it the wrong way. Yeah.
When you do the 1 minus whatever the number is, do you also, you know how you put the line from the, where you start on one side to put
The area?
yeah, so do you do the same on the other side? I mean the side that you're not looking for. The one that's not shaded.
Yeah, that's exactly what that is, right? Okay. Why did I put that there? Because the book only tells you areas that are below. And then we do this because we're like, we don't want that. We want the area above. Cool. So the minute you look up an area from the chart, you put that below what you just looked up because that's all it tells you. And it makes sense because this is definitely more than half of the picture. So the answer can't be 30.5%. That makes no sense. This is a big old chunk of this picture. Should be over 50%. So right there you should go, well shit, if I put that over there, it makes no sense. Alright, real quick. Do this wrong, and then we'll do it. We'll get the exact answer from the expensive ass calculator. Should be able to do this for us. So to do it wrong, I would forget to change this number. I would forget that it's discrete. I hate this. So what I would do is I'd do this. And like I said, maybe don't even write this down. 27. I would forget to put my little bar. I would change this to a z-score. 27. 20.56. Whatever that is.
Negative 0.38.
Negative 0.38. So when I look up negative 0.38, what do you get?
0.3520.
3520. So this will be 0.648. Is that different from what we got here? And that's actually off by almost 5%. That's pretty big. That's a pretty big difference, right? You guys, so the mistake I made here was I forgot to change the 27 to be one side of the rectangle. All right, now here's where I get a little bit nervous as a teacher. I didn't do this problem beforehand, so let's do it correctly. Let's do it using the binomial. We don't want to do the binomial ourselves, do we? Because that meant 27, 28, 29, up to 68. Screw it. The calculator can eat it for lunch because it's what it does. So we're going to have the calculator actually do it using the binomial directly. And I might even show you. There you go. In the process, this is important because you guys can copy down the process. Let me get that real quick. Look at that. Okay. And again, everything we're about to do is on that calculator Bible, as always. Showing me your work is not showing me the buttons you pressed. It's not good enough, right? Okay, here we go. So if you go to, if it's second var, see how above the second var it says DISTR, it stands for distributions? Sounds vaguely familiar. Maybe I've come in here before. See the very first thing it talks about is normal? There's an example of how to do a normal distribution using the calculator. I have that on the calculator Bible. Right now I want to find binomial. So if you hit the up arrow, it's actually quicker. Here's binomial. Now there's two options here. PDF, P stands for particular. So if I want like exactly 7 successes or something, then I could do binomial PDF for a particular value. CDF is cumulative. So if I want from 0 up to something successes, I need to use this. CDF always goes from 0 up to something. Okay? Here's your inputs. So I definitely want to use binomial CDF for cumulative. It always goes from 0 up to something. What kind of sucks then about my problem? My problem goes from 27 up to 68, right? How do I get this number here, though? I would go from 0 up to what?
26.
Careful. 26. Cool? Do you guys see that? What's on this side? It must be 0 up to 26 because this is 27 and up. So if I put into my CDF, if I tell it to do up to 26, that number better be close to this. It's not going to be close to this because this is where I made a mistake, right? So how do I put this stuff in? So binomial CDF, what do you think I have to tell the calculator? What do I have to know to do this problem? I have to know N and P. And why do you think I really don't have to tell it Q? Because it eats calculations for lunch. If you tell it P, then it can calculate its own damn Q, right? Paid enough money to exist. Do the work for me, please. So the inputs for binomial CDF are always N, comma, punctuation on the calculator, P, comma, X. The number of successes you want to go up to in this case, right? So in this case, what's N?
68.
68, comma, what's P? 0.42. And then I want to go up to 26.
You said NPX?
N, comma, P, comma, X. And again, that's on the calculator Bible, which if you lost it, go to the website, print it out again. If I'm you, I'm going to have that bad boy sit next to me all the damn time as I do homework. Yeah.
I updated my software, so like.
Oh, it asks you the pieces?
Is this what I have it in here?
Yeah, so NPX. Same thing, they just did it in a different format. Cool. I like it. 0.3082. So which one is that closer to? 0.3050 or 0.3520? Yeah, the one that I did it correctly, right? If you forget to change this number because you have a discrete distribution that you're trying to use a continuous for, you will be way the hell off from the right answer. Am I exactly right? Why doesn't it matter? I've already told you it's a freaking approximation, right? I've already told you ahead of time. Oh, I'm not that sure about this. Yeah.
If you do something like this and then decide to use a calculator and check it, do you change the number? Or do you
Yeah, now what's the true probability? I want to make sure you guys understand. The same thing I had to do here, really. Didn't we get this number first? And then I have to do a 1 minus? So how do I get the real answer here? 1 minus to get the other side. So what's 1 minus, and you guys remember this? Second negative, 1 minus the last thing on the screen? 0.6917. And what we got there was 0.695. That's pretty damn close. How are we doing so far? Is that?
How do you do that? 1 minus what?
And then answer is really a cool button because it has in memory the last number that showed up on the screen. So 1 minus second negative button down here, see? And a little A and S should show up on the screen. All right, how are you guys doing? Yes, ma'am.
So why do we put in 26 up there, but we got like 26.5?
Why do these numbers exist in the first place? These two? Because I'm using a z-score. I'm using a normal distribution for a binomial problem. In the calculator, I'm using the binomial, right? Do I have to change any numbers then? Am I approximating a binomial? No, this is a binomial. I should put in the real number.
Isn't the real number 27?
No. This side is 27 and up, so what's this side? 26 and down.
I see.
So I really want you to understand. CDF always goes from what? Up. From 0 up. Right? That's how it's hardwired. So if I want to go from 27 up, I've got to do 1 minus from 0 to 26. Right? The opposite. Cool. Yes?
It's weird. I mean, I've got the same answer you have for the first one, but then when I did second minus, I got the exact same thing on that side. I mean, here.
Because you did 1 minus 0.3050 for some reason.
It actually did myself.
Here, wait. There. Then 1 minus second answer. Okay. I'm not sure what
Yeah, I
happened.
do that. I just
I'm not
did
sure how the 0.3050 would get in there.
Yeah, he did it by himself. I didn't put it on there.
It's messing with you. They do that sometimes.
We're not passing that cake.
Karma the next day. I love it. Okay. So just to show you a quick example of PDF. If I had this set up here, so this is always NPX. If I had, so 42% again, and we have 68 San Diegans, I want to know the probability that exactly 30 give out candy, right? Let's do it both ways. How would I set up the, oh, thank you. I tell you, I need to pay a cameraman. We're going to do it the incredibly correct way, because we're going to use the how would I set up the formula, the probability formula? What would that look like? How many people do I have? 68. Choose. 0.42 and how many of those? 30. You just told yourself 30. And then how many 0.58s?
38.
The rest. I like it. So let's do that real quick. 68. Math. Where'd I go? Probability. The third one. 68. Choose 30. I don't know how to do all that. Times 0.42 to the 30th. Times 0.58 to the 38. The rest of them.
Can you do it for me again?
Certainly. 68.
No, I have to get to that. Okay, 68.
Math. Probability. And then the third one down is NCI. That's my choose, right? Choose 30. Is that okay? All right, thank you. I don't want to do it all over
Thank you
again.
very much.
Anytime. How are we doing so far? Is that cool? Yeah. And I will need to see this setup, right? To check ourselves, what can I put into Binomial PDF? Go to second vars to get the distributions. Go to Binomial PDF. Why am I using PDF now? Particular. I want exactly 30. It's a particular number, not an accumulative number, not a lot of numbers, right? Just 30. So particularly 30. What are my inputs here?
68.
N, good, 68. 0.42 for P. And I want exactly 30. Same damn number, right? Of course it is. Because what's the calculator do? It does that formula. Ooh, so of course it's going to be exactly the same number, right? The problem is, the reason I don't just teach this is because then you guys have no connection to what the hell's going on. I'll put it in a little black box and it tells me this. Yay. It's no good. At least here you can see what goes into making it, and actually hopefully makes sense. 30 of these, the rest are failures. This tells me how many ways to do it. You can see the parts that go into it, not just it come out of box, right? Okay. So I think that's all I want to say officially on 6.6. So now I can just open it up to whatever you guys want to look at specifically. If I'm you and I really don't have any questions right now, I'd be correcting that quiz, for one thing. The average on that thing was a 74. I can't remember the standard deviation, but it was kind of large because I had somebody got 100, and somebody got 30 something. So it was all over. Yeah.
Did you do in section 6.3 number 2?
So on page 259, number 2. Oh, okay. So this one says the distribution of IQ scores of a mean of 100 and a standard deviation of 15.
Yes.
You guys ever seen Forrest Gump?
Yes.
Mm-hmm.
And they say that he's got an IQ so low it's below so many standard deviations away. That's how they kind of define certain levels of mental ability, right? And so if you go the other way, you have groups like Mensa that say, oh, if you got a really high IQ, come and join us. IQ is just your potential. It has no relationship to how smart you actually are, which is kind of funny. So if you know your IQ, you can kind of figure out how many z-scores above or below the mean you are. The question, though, is more general. What's the area under this whole curve? And what goes right in the middle?
100.
What's this whole area? Gotta be 1 or 100%. That's the idea. If you add all the probabilities up, the probability somebody's got a 101, 102, 90, 99, if you add them all up, it's got to be 1. So the area under the curve is 1. That's why if I had a piece of it that was, if this is 10% of the whole picture, then the area in there is 10%. That's the connection. Area is probability then, as long as the whole area is 1. The percentage of the area, that's the probability that you're in there. It's just like the bullseye. What about part B? What's the value of the median? What do you think? What's right in the middle of the data? 100. No question about it, because the picture is symmetric, right? If I cut it down the middle and fold it on top of itself, it's symmetric. So that means the median must be in the middle also. The median equals the mean equals 100. What about the mode? What occurs the most? 100, because that's the highest part of it, isn't it? So the mode is the median, is the mean. is 100. So the normal distribution is one of the few distributions that actually has this property. These three are the same value. Because the mode is where it's the highest, because that's the most. That's 100. The mean is the number that's the average of everything. It's in the middle for normal distribution. That's the mean. And the median is the one that has 50% above it and 50% below it. Well, that's the mean. So they're all the same number. So that's one really basic property of the normal distribution. That. All three of those are right in the middle.
And we do a couple from 3, 4.
From where?
From 3, 4. That's gonna be
Oh, 3, 4. Well, let me see. Before I go to 3, 4, any other questions from 6?
On the same section, number 4.
Oh, where was I? 6,
3.
3? Oh, yeah. If I have a computer randomly generate digits from 0 to 9, is that going to be a normal distribution? What's the average of the numbers then?
9. 0 to 9.
If I have from 0 to 9,
4, 5.
so let's see.
Add it up.
So if I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? And so I've got 10 numbers up there. So what's the, so let's see, this is 4 things here, and this is 4 things here. Yeah, so right there it's going to be right in the middle of those two, right? But why am I doing that? How do I know I can just add them up and divide by how many there are to see what the average is? Because each of those numbers, are any of them more likely to happen?
No, they're all equally likely.
They're all equally likely. So right there, will it look normal? Will it have a high thing in the middle
No.
and the other ones at the end are unlikely? No. This is going to be this. They're all equally likely, right? That does not look normal at all. Cool. So then it says, find the probability that when one digit is randomly generated is less than 5. Can you use the methods of this section? Well, this section is all about normal. That's not normal, so no, right? How do you figure out the probability that it's less than 5? Well, how many digits are there?
just 5.
10.
10. And out of those 10, since they're all equally likely, how many are less than 5?
5.
5 out of 10 is 50% chance. All right, you can't do that with a normal distribution because they get less and less likely back here. They're more likely near the mean. Okay, maybe. Okay. But that one, when you first read through it, it is a little weird because you kind of want to say, yeah, why not? You could draw the picture, but the picture's got to make sense. Is the mean the most likely thing? No, they're all equally likely. Yeah.
Can you touch on 6.6, number 30?
Number
30?
30. Oh, okay. So the key there, 30 is a little weird when you first read through it. So everybody kind of read through it, page 296. Oh. You know, I meant to make a big deal out of this earlier, and then I totally skipped it. We had a problem earlier where we had to figure out the mean and the standard deviation for the binomial, and then we use z-scores. And again, this is going to be another part of the problem, just like on the practice test. What do we have to check before we can actually use z-scores? Yeah, if NP and NQ are bigger than 5, because I can't use the chart unless I know that my distribution is normal enough. And if NP and NQ are both bigger than 5, which it would have been for that problem we did, then I can use the z-score chart because it's normal enough, right? So what do you guys think about number 30? It's a little strange, to say the least. You missed your stop. Let's see. So number 30. So the weird thing about number 30 is they tell you this 15 out of 57 number, which kind of throws people off. Assuming that the polygraph makes random guesses. Determine whether 15 is an unusually low number of false positive results. So if it makes random guesses, what percentage of the time should it be wrong, is what I really want to ask you.
Can we assume this proportion, 15 or 57, as a probability of...
See, that's too specific. That number they give you is based off of something they actually saw, right? So they can do the 15 out of 57 based on what they saw.
That's why the answer is...
Now they're saying, let's compare what we saw to theoretically what would happen if it was actually making random guesses, right? And what is 15 divided by 57, just out of curiosity?
0.260.
Okay. Now here's the weird part. Here's the part that I agree with you is kind of weird. What could happen in this example? It could be right. How many ways could it be correct? Because what could the polygraph say? It could say you're lying, or it could say you're telling the truth, right? So there's those things. So it could say you're lying or you're telling the truth, is what it could say. And what could actually be happening? You could actually be lying, or you could actually be telling the truth. So what percentage of the time will it say you're lying when you actually aren't? A quarter of the time. I love it. Because how many things up here are there that could happen? It could be wrong. Here is wrong, and here is wrong. Here's right. Here's right. So how many total things could happen? How many total things could happen? 1, 2, 3, 4. Out of those 4 times, how often is it wrong in a certain way? It said you lied, but you didn't. So 4 things that could happen. And how many times does it say that you were lying, but you were actually telling the truth? 1 out of 4, so 25%. So what they're trying to say then is the 15 out of 57 actually ends up being close to 25%. Do you see what I'm saying? So, yeah. So this is, there's only one way to do that. 1 out of 4 is 25%. So now let go of the 15 out of 57. You're testing that. Theoretically, it should be 25% if it's making random guesses. So now you're going to see is 15, how unlikely is it to be around that point, right? So then P would be 0.25. Q is 0.75. If you make P equal to what 15 divided by 57 is, you're artificially making 15 the most likely thing. So of course it's going to come out, oh wow, looks good. That's no, yeah, I want to test it based on what it theoretically what it would do.
So N would be 1/4 or 4?
No. What's N? How many times did they do it?
Oh, okay, okay.
57. N has got to be a whole number, definitely. I can't, yeah. It's got to be a whole number of times I'm doing something.
Okay.
And I want to know the probability of what?
Less than or equal to...
And actually, this is, I would do this problem differently than I think they want you to tell you honestly. And here, this is getting into something that, sorry, 10:30. Let me see if I can get you guys to understand this, because what do we do, this problem, this is actually good. What do we do with this problem if I just gave you this? I wouldn't use a z-score for this problem. How could you tell us something's unusual? Find the what, and the what. The min and the max, right? The expected value minus a couple standard deviations plus a couple standard deviations. So anything outside of that would be unusual. So when I have a specific data value, what's kind of what's kind of unfair is, let me ask you this, how unusual would it be? Would it be unusual to go out and find a dude that weighed 170 pounds? No. But really think about it. Why is that true? Is it because the number 170.00000 occurs a lot, or because 170 is in an area where a lot of people are? It's in the area where a lot of people are. So if I said, is it unusual for somebody to weigh 170.58296? Technically, yes, because not a lot of people weigh exactly that. Are you with me? But in a way, that's not the way I want to look at it. I want to say, no, he's about 170 pounds. That's not unusual. It's right where it should be. So when I want to check, real quick, what's the mean here so I can put it on the picture? So it'll be a quarter of 57. It's like 14 point something. 14.25. So that's the mean. To see if 15 is unusual, what I would actually do is see, here's 15, and I'd see what's the area 15 and up. So actually I want to start on this side. That'll be later. I want to see what's in that area there. Because, for example, would it be unusual to go out and find a dude that weighs 300 pounds? Randomly. Just go out and randomly, and he weighs 300 pounds. Around 300 pounds, right? Because anybody above like 220 or 240 or whatever that would be considered unusual to do it randomly and pick somebody that would actually be above that weight. You guys kind of with me? Not because the number 300 is unusual, but because the region that number's in is unusual, right? So if I want to know, is 15 unusual, I want to see, well, is 15 and up, is that number, is that percentage less than 5%? Is that area unusual for somebody to be in? So really the question on this problem then is x greater than or equal to 15. Find that probability. If it's less than 5%, then yes, it's unusual. So before now, we were talking about individual values being usual or not. But in reality, we were talking about regions where they become unusual and regions where they are usual, right? So now we're just being more specific about that idea. I don't want to just look at 15 and find out its probability. That's not fair. I want to look at 15 and up. So that should actually get you started on the problem. Is that cool? Because now you can do the continuity correction and all that kind of business. So let me give you another example of this, what I'm talking about. This is I like this example here. This is kind of getting us in the direction of what we're going to be doing in the next chapter. There you are. If I flip a coin 2,000 times, and I'm looking for tails, right? What's the average number of tails I should see?
1,000.
Exactly. It'd be NP 2,000 times a half is 1,000. What's the other name for mean? I like that. Not average. Even more? We learned in chapter 5. It looks sort of like the formula for expected value. I like it. Right? EXP, expected value. Which means that it's the value that should have what kind of probability?
Highest.
The highest probability. It should be the highest probability thing. Now here's the funny thing. Let me see if you guys can do this down the calculator. Can you figure out the probability that x is exactly 1,000 using binomial PDF? Because probably the 2,000 choose 1,000, your calculator would probably say overflow error. It's like, holy shit, that's a lot. It's too much I can handle. So let's try to use binomial PDF. What would I throw in there to do this? What's n? 2,000. What's p? 0.5. And what's x? 1,000. It should be the most likely thing. It is the most likely thing. But what's the probability that I get exactly 1,000? I'll do it up here. Second vars, binomial PDF. Shoot. All right, there you go. 2,000, 0.5, 1,000. So the probability that I get 1,000 is 0.018. Let's say 1.8% roughly. You guys with me? Now what's weird about that? Would you technically then say that it's unusual to get 1,000?
Yeah.
Yes. But why is that unfair? 1,000 is supposed to be the expected value because you would expect, and it's going to be kind of a wide, flat, that's why it doesn't go up very high. 1,000's right there. It should be the most likely. Because things in this area are what should happen, right? It's not fair to just point out 1,000. Oh, it's only 1.8% chance of happening. But every single other probability you calculate will be less than this. They all still have to add up to be 100, right? And they will because there's so freaking many of them. From 0 to 2,000. They're all going to add up to 100%. It's just that each one is really small chance. I don't know if you guys kind of get what I'm saying here. It's not fair to look at a single value and say, that means that's unusual. So if somebody flipped a coin 2,000 times and got 1,000 tails, you wouldn't go, holy shit. Because you're like, well, that's around that should happen. Around that should happen, I don't care. If they flipped 3 tails, then you go, holy shit, what are you doing with all your time? Or, I mean, 3 tails out of 2,000 is weird, right? Because it shouldn't happen in that area. It should happen in this area, most likely. Desperately hoping. How much do you really have to understand everything I just said for this test? Not. Right? But it's going to become really crucial in the next couple chapters. All right, so we got a few more minutes here. Anything else you want to focus on? Oh, yeah, we got to go back to box plots too, right? Yeah.
18 in 6, 5.
So we'll do this, and then we'll look at a box plot problem, and then we'll call it a day. 18? Let's see. All right. So this would be a good review. We haven't done a problem yet where you have a sample of stuff, and you're asking about the sample mean. What's got to change then when I take a sample of stuff and I ask about the sample mean? What do you have to change? Standard deviation has to change, right? Because the picture suddenly becomes skinnier. Everything rushes to the middle. The standard deviation should get smaller. So that's this kind of problem here. Okay. So this one says, curly quarters have weights that are normally distributed with a mean of 5.67 grams. Standard deviation of 0.062. The vending machine is configured to accept only those quarters with weights between that and that. To 5.79 grams. And the reason they do this is they don't want a lot of people to be pissed off if it doesn't take their quarter.